Hi guys, in this session we will learn about a very interesting topic called colorimetry. And this colorimetry is an instrumental technique. It is an instrumental technique where you can see the different instrumental techniques that are available. So we have you might come across the different techniques like conductometric titrations, then pH metric titrations, then potentiometric titrations, and finally colorimetry. So normally if we consider these three titrations, okay, they can be done in the range of 0.05 molar to 0.1 molar. But seriously, in the case of colorimetry, it will be different. Maybe they will be ranging from grams to few milligrams. But whereas in the case of colorimetry, it will be very less. Maybe from in the range of microgram to nanogram, or still it may start from milligram to microgram, then to nanogram. So the range of colorimetry will be different. So what is this actual colorimetry? So colorimetry, it is nothing but, if I try to divide the words color and metry. Metry means measurement. What is metry? Metry means measurement. Then color. So what is this color? Measurement of this color. So it is nothing but measurement of color intensity. Color. So what is that we measure for color? Color intensity. In this case, what happens is concentration is made as a function. Concentration is made as a function of color intensity. So let us try to define colorimetry. So colorimetry is measurement of concentration. So it is measurement of concentration as a function of color intensity. So this is the exact definition. What is colorimetry? It is the measurement of concentration as a function of color intensity. So now let us see what is color. So what is color? I hope you have an idea about color. So what is color? Color is the property, color is the property of emission or absorption, or rather emission or reflection. So what is color? Color is the property of emission or reflection, right? If I take light, so this light, so now what is light? So light is a form of energy, we all know about that. Now this light has been divided into two types. So first one is called polarized light and another one is unpolarized light. First one is polarized light and another one is unpolarized light. That means this polarized light, it moves only in one direction. Whereas the unpolarized light, it moves in all directions. So you can see like this over here. So this light moves only in one direction, whereas this is the unpolarized light. The above one is a polarized light and this one is the unpolarized light. So this light moves in all directions. Now what happens when this white light is made to pass through a prism? What happens when the white light is made to pass through a prism? I hope you know about prism. Pass through a prism. So let us see what happens. So this is the prism. Now white light is made to pass through the prism. This white light is made to pass through the prism. So this white light will split into its 7 component colors. So this white light is made to pass through this prism. Then it will split into the 7 component colors. So usually this phenomenon is known as dispersion of light. So whenever this white light is made to pass through the prism, it will split into its 7 component colors, that is VIBGR, violet, indigo, blue, green, yellow, orange and red. So this phenomenon is known as dispersion of light. So here what happens is, this dispersion of light produces 7 colors. This dispersion phenomenon produce 7 colors, 7 different colors. Okay, so these 7 different colors, they will be ranging in from 400 nanometer to 700 nanometer. They will be ranging from 400 nanometer to 700 nanometer. So the 7 different colors will be ranging from 400 nanometer to 700 nanometer. And next is disk experiment, wherein a round cardboard is taken and this is divided into different regions, just like this. V, I, B, G, Y, O, R. Right? So this is divided into the 7 component regions. Now what happens is, if I spin this disk, if I spin the disk, so now what happens, on a whole it appears to be white. It appears to be white. So when I try to spin the disk, it appears to be white. And when a system or a molecule, absorbs in one particular region, when a system or molecule absorbs energy in one particular region, it emits the energy in its complementary region. It emits the energy in its complementary region. How? This is a very important statement to remember. When a system or a molecule absorbs energy in one particular region, it emits the energy in its complementary region. This is very important. For example, if I say that if the absorption of the energy is there in violet color region, then it emits the energy in yellow color region. It emits the energy in yellow color region. This is how the emission and absorption will take place. So if a system appears, it absorbs in the violet color region, then obviously it emits in the yellow color region, that is its complementary region. Okay. Now we have to learn another important topic, that is nothing but when a radiation is made to fall on a molecule, what happens? So what happens when a radiation is made to fall on a molecule? Normally in any system you can find the two different energy levels. Okay, so this is energy level E1 and this is energy level E2. Now this system is irradiated with an energy h nu, and in this always the condition is E2 is greater than E1. This is one condition, and this system is irradiated with the energy h nu. What happens? The molecules which are present in the lower energy state, that is E1, will absorb the energy and go to the higher energy state. So the molecules in the lower energy state will absorb the energy and go to the higher energy state. Does they stay there? No, they don't stay there. Okay, again they come back to the original, ground state. So again they emit the energy in the form of h nu prime. Okay, and remember, h nu is always greater than h nu prime. And delta E, the energy difference between the two energy levels, is given by E2 minus E1. Delta E is given by E2 minus E1, or delta E is equal to Hc by lambda. So what is this? Lambda is wavelength. So this depends on the excitation, or rather the emission. Emission depends upon the wavelength. Okay, usually. So this is the condition where E1 is the ground state and E2 is the excited state. So the energy is absorbed, and again the molecule will not be there in the excited state, so it will come down to the ground state and emit the energy h nu prime, and always the incident energy will be more than the emitted energy. Incident energy will be more than the emitted energy. Now let us look at the coming to the actual experiment. So let us look at the important thing, that is principle of colorimetry. Principle of colorimetry. So what is this principle of colorimetry? Okay, so here this colorimetry experiment, it is based on Beer-Lambert's law. It is based on Beer-Lambert's law. So we will learn about this in unit number 5. So I'll be giving you an overview now. We will learn in depth. Okay, it is based on Beer-Lambert's law, where Beer-Lambert's law is a combination of two laws. One is known as Beer's law and another one is Lambert's law. Beer's law and another one is Lambert's law. What does Beer's law states? Beer's law states that absorbance is proportional to concentration, that is C, and Lambert's law states that absorbance is proportional to path length. Absorbance is proportional to path length. So if I try to combine both, A is proportional to C into L, or A is equal to epsilon into C into L. A is equal to epsilon into C into L, where epsilon is a proportionality constant. Epsilon is proportionality constant. Then it is also known as molar absorptivity. It is also known as molar absorptivity or molar extinction coefficient. It is known as molar absorptivity or molar extinction coefficient. Okay, so in general, what happens is, this colorimetry is principally used for calculating the concentration of metals. This colorimetry is principally used for calculating the concentration of metals. If I take metals, few of them are colored. Few are colored. For example, like potassium dichromate, it is colored, or potassium permanganate, and few are colorless. Few of them are colored and few of them are colorless. Example, calcium 2+, magnesium 2+, zinc. Okay, so these are colorless. Few of them are colored. So in general, in order to determine the metals, concentration of metals in the sense, so what we do is we try to react with the metal. We try to react the metal with a ligand. Usually this metal is colorless, and then we try to react that with a ligand. Then they form metal ligand complex, which is a colored complex. They form metal ligand colored complex. So what is this a ligand? What is this ligand? It is a species which is capable of donating the electrons. It is a species which is capable of donating the electrons. This is the definition. And the nature, if I look at the nature of the ligand, it may be organic, or inorganic in nature, and it may be charged or neutral. It may be charged or it may be neutral. Now what happens if I take so I have taken this metal ligand complex. What is this? This is the metal ligand complex or a solution in a vessel having a path length L, and a light of intensity I0 is incident on it. Light of intensity I0 is incident on it. Then what happens? So here a part of light, so different phenomenon take place at this point. So obviously we all know a part of light will be transmitted. And in this case I0 is always greater than IT. Intensity of incident light is greater than intensity of transmitted light. But what happened to the difference of the intensities? So usually what happens is, whenever the light of intensity I0 is incident on it, a part of light is absorbed, a part of light is reflected, a part of light is scattered, and finally a part of light is transmitted. So these four phenomena take place whenever the light is incident. So the intensity of incident light is equal to intensity of absorption, intensity of reflection, intensity due to scattering, and intensity due to transmission. And always effects due to I absorption and effects due to I reflection and I scattering are minimum. So effects due to intensity, reflection and scattering, they are minimum. So always what happens? I0 is equal to IA plus IT. So intensity of incident light is always equal to intensity of absorbed light and intensity of the transmitted light, So from the above expression, so intensity of absorbed light is equal to intensity of incident light minus intensity of transmitted light. Intensity of absorbed light is equal to intensity of incident light minus intensity of transmitted light. So from this Beer-Lambert's law has been derived. From this Beer-Lambert's law have been derived. So this is in detail about the theory behind the experiment. Now